Hey, welcome back to Math with Patrick. Today is September 4th, and we're solving problem 247 from the Daily Epsilon calendar. And today looks like we have some kind of geometry problem. I see that we have two circles. I'm going to redraw it because I'd rather this line be flat. We have two circles, both of which have a radius of 5. And then kind of between them, also it looks like the circles are supposed to be tangent to each other right here, like just barely touching at one point. Also, that one point should be at the same height as the centers of the circles, so it should look a bit more like that. Anyways, and then between the two circles, it also looks like we have another shape that's, I guess you could say, tangent to the other two, where it's intersecting or just kind of crossing at one point there in the corners. And based on these 4 tick marks on the edges there, I'm pretty sure that it's supposed to be a square. I also see the right angles there and there, so definitely a square. And once we find the area of the square, it's supposed to match today's date. And since today's the 4th, the area of this square should be 4. Let's figure out why. So let's say we think of other quadrilaterals that could kind of fit right here, where we have like 2 corners on either of the circles and 2 corners on this baseline. I'm kind of seeing how like this could be interpreted as a rectangle. Like let's say for a sec that it is, right? Then maybe instead of kind of it, well, being a square, we could have, say, a rectangle that looks more like this. Because it's still kind of following the general rules of like kind of touching the circles at one point and still being on this baseline. I guess it could also be a bit taller, kind of like this, still touching the circles one each, and then both of these bottom points being on that flat baseline. And the reason why I'm kind of talking about this is like, I want to see if I can kind of figure out when this thing turns into a square. Like, what's this magical moment as we take this kind of flat rectangle and bring it up to a square, and then it'll go on to like a thinner rectangle, kind of in this example right here. But I want to know like the exact moment or like what numbers are happening when this quadrilateral turns from a rectangle into a square. And I think that would let me then deduce that this side length is 2 and 2, and then finding the area of that square would just be 4. So hopefully I can find some kind of way to prove that yes, this length or this length should be 2. So my first thought is I need to assign a variable somewhere. I think what would make the most sense to me is if I assign this length from this point to some variable. On my other pictures, it would be maybe shorter there or maybe longer here. I'm just going to call it A for kind of simplicity, I suppose. And I know that A could range from 0 to 5, right? Because if it's 0, then I have basically something that looks even flatter than this. It would just be like a flat rectangle right here. And let me maybe put some thoughts in a table. So if my new variable A is equal to 0, then maybe I'll do like length and width for my square / rectangle. When my A is 0, the length is going to be all the way from here to here, and that's a length of 10. It's basically both radii added to each other. So the length could be 10, and the width is obviously 0. And the reason why I'm like kind of doing these test points is I do want to make some kind of like algebraic expression that relates the length and the width and this A value that I'm doing, and it should go back and make sense for these points that I'm creating in this table. So likewise, if A is 5, that means I've kind of gone all the way this way. And so I'm more in a scenario over here, but it's just straight up and down. There's going to be no length at all. And so A could possibly be 5. The length would be 0. And I guess the height, honestly, of the rectangle, let's just keep it as a W, is going to be 5 because it's equal to the radii. So there is some kind of mysterious intermediate value. Like see how like the length goes down and the width goes up. There's going to be some mysterious intermediate value where these are both equal to each other. Based on the picture and knowing that the answer is 4, I know that that means length and width are both going to be 2. That means A is going to be equal to 4, right? Because this would be a 4, and that length right here would be a 1. So essentially, I just need to prove that this mystery should be the number 4, and then that would make these both equal to each other. I don't see it just yet. So let me make some kind of expression, some kind of function rather, where I plug in the A and I get the length. Let's do L first. I think L will be easier. I'm pretty sure this is just some kind of linear function here. Basically, as A takes up some space, it'll actually take up space on both sides. So here and here will be the same length A. And L is just what I have left over from the whole length. And this whole length we already saw was 10. And so when I scale A up a little bit, I'll be subtracting A twice from that length of 10. And then now I have some kind of expression for my length. I think the width, or I guess technically the height maybe of the rectangle is going to be a bit harder. I still want to express it as some function in terms of A though. That way, when I set the length and the width equal to each other, then I'll be able to solve for A over here. So somehow moving this A this way is going to increase my width by some amount. I think I should do a circle equation maybe, where I guess I could pretend that this point right here is like the origin on a graph. And this would be my A axis, and this would be my W axis. And I know that the general circle equation using A and W is going to be A squared plus W squared equals the radius squared. The radius on the circle is 5, so there should be a 25 right here. And this equation, though, would have the circle center the origin, and I want to move it 5 units up in the W direction. So using a little bit of graph transformations, I could do W minus 5 instead of just the W. And I believe this will move the circle up 5 units. Just to be sure, I want to make sure that if I plug in 0, 0, the origin, I do get a point on that circle. And that would look like me plugging in a 0 here and here and getting an equation that is true. Well, if A squared is, or if A is 0, A squared is 0. And then if W is 0, then I get this negative 5 squared. And this is equal to 25 because that's the number 25. And so I trust this equation. Now I'm sure I could like test out more points. Like I could plug in the point like right here. This would be 5, 5. And yep, that still works because then this becomes a 25, this becomes a 0, and 25 plus 0 is 25. Okay, cool. So now I have some kind of relationship between this A length and the W length. And so I guess all I need to do is isolate A, then I'll get some kind of expression here, which should be equal to W. So I guess, I could just do, like subtract this whole term from both sides, so 25 minus W minus 5 squared. And I'm wondering if I should expand that out, or if I should just keep it by itself. I don't really know just yet. I'll keep it alone for now. So I'll square root both sides. We're going to get 25 minus W minus 5 squared. And I guess after square rooting stuff, I do know that I kind of like get rid of half of the circle, and I actually don't know which side I just got rid of. That might actually pose an issue. So how do I figure that out? I know now that A can no longer be negative in this case, because I know that square roots don't return negative values. So I think that's what I did. I just basically ruined this circle and turned it into a semicircle by making A no longer be able to be negative, which I guess is fine, because that kind of rules out this side of the circle. And so this equation is still true on the other side of the circle, and that happens to be the one that I'm actually caring about for this problem. So I think this expression is fine. Now I have a function that helps me go between A and W, and I just did it backwards. Duh. I wanted to solve for W. It's W equals. Oh my goodness. So let me try that again. Let's isolate the W. And how should we do this? Let's subtract the A squared from both sides. Let's hit both sides with a square root. that means now that w minus 5 is greater than or equal to 0, right? Because same thing, square roots can't return negative values. So I'm just keeping this in mind just to make sure that it makes or doesn't make sense for my problem. Actually, let's check that now. W minus 5 is greater than 0, so this means w is greater than 5. Is that okay? Ooh, that's really not okay, actually, because w equals 5 is going to be right here. And so w being greater than 5 means I'm only keeping this kind of top half of the circle. Or, yeah, it would turn into a semicircle. But I really only want the bottom part, because this is the problem that's helping me, or this is the part of the circle that's helping me solve the problem. So instead, looking here, I think I actually need a negative sign somewhere, because once you're the one to impose a square root on an equation as like an algebra step, usually you put a plus and minus sign. But here I think I just want the minus, because I think that would give me the bottom half of the circle. Okay, hopefully that worked. I'll add 5 to both sides, so w is going to be equal to 5 minus, and then square root 25 minus a squared. There we go. Let's put that there. And I guess I should test a point out just to be careful. Like, it looks like when a is equal to 5, then w is also equal to 5. Like, this is what I was talking about with like setting up this table, right? These functions should work for the obvious points, and then it'll help me with the non-obvious points. So if I do plug in a 5 right there, I do get the square root of 0, and then 5 minus 0 is still 5. So I do trust these equations. Cool. Well, I think I got my setup then. I just want to know when the length and the width are equal. That makes it a square. So I could just set these equal to each other and solve for a. Not too bad. I mean, we'll see. 10 minus 2a equals 5 minus root 25 minus a squared. Let's simplify with the 5s. I'll at least subtract 5 from both sides. There's still a negative sign. And then I don't like dealing with negatives, so I'm going to add the 2a over here, and I'm going to add this root 25 minus a squared over there. And I guess to really solve for a, I think I'll need to release a square root sign. So actually, let's subtract that 5 and put it over here. This way I isolated my square root expression, and now I can take the square of both sides. So 25 minus a squared is equal to this squared. And then maybe if we expand the right side, we could solve down to a quadratic. Let's see, 4a squared, and then it's going to be plus 25 on the end, and then minus twice this product, so that's going to be minus 20a. Over on the left side, we still have 25 minus a squared. Let's set it equal to 0. That's usually a good strategy with quadratics. We're going to add the a squared over here. We're going to subtract the 25 from both sides, so these both go away. And now we could factor out a 5, or I guess I could just divide both sides by 5 as well, and that's not going to change the left side. So a squared minus 4a. Let's do some factoring, factor an a out, and then now I have a product. I have something times something is 0, so surely one of them is 0. Either this first number could totally be 0, right, because 0 times anything is still 0, or this right factor needs to be 0, and thus a would have to be 4. So from a quadratic, I'm getting 2 potential solutions, and these potential solutions are supposed to explain when the length and the width are equal. But we can go back and double check this example of a equals 0, and just kind of based on like this initial point right here, clearly a is not equal to 0, because clearly that makes the length 10 and the width 0. So I can kind of treat this as an extraneous solution, get rid of it, and then we could test what happens when a is equal to 4. Maybe let's use these functions that I wrote from earlier. I mean, here I can kind of clearly see that we plug in a 4 for a, we just get 10 minus 2 times 4, or 10 minus 8, which makes the length 2. And this is when, a is 4 right here. And then when we plug in a 4 right here, we do get 5 minus root 25 minus 16. 25 minus 16 is 9. And then the square root of 9 is equal to 3. And then finally, 5 minus 3 is equal to 2. So great. Essentially, by testing out different quadrilaterals, or I guess different rectangles, and just waiting for the perfect moment for the rectangle to turn into a square, we know that this A length is now 4. So this length from here to here must be 4. Symmetrically, that means this length is also 4. And then finally, because we have a radius here and here, this whole green length is 10. And that tells us that our side length right there is 2. And then since it's a square, to find its area, we do essentially just the side length squared, and that gives us 4 for today. So there at least is my solution. Maybe there's a better one, thinking more like geometrically than algebraically with function notation, but this is the best way that I found. And I hope you enjoyed the solution. So thanks for watching, as always, and I will see you tomorrow. Bye.